This is IndexedState for safer functional APIs. And we'll start with, who am I? I'm Vincent Marquez. That's my Twitter handle. If you guys want to argue with me about functional programming, I encourage it. That's my GitHub. So I'm currently working at Verizon Labs. I'm a ScholarZ contributor committer, Hazelcast contributor, and maybe an Scoda contributor. Where's Michael Pilquist? Merge my pull request. All right, so I build a lot of APIs for my coworkers. And this is going to be kind of a basic API that I might have done a couple years ago, and we're going to talk about how we could improve it. So here we have this idea of a connection. And we can do some things to the connection, right? We can set the destination, we can initialize some credentials, we can connect, we can send data. But while I'm not going to say this API is bad, I'm going to say that I think we can improve it, right? The types don't give us a lot of information. They don't tell us how long things take, if something's happening asynchronously. They don't tell us if something's mutating, and we are mutating things, or at least changing things, right? The state of the connection's changing. We start with an unconnected state of the connection, and then we're going to go to a connected state. We're going to be in a state that we haven't sent any data, and then we're going to have a state of the connection where we either already sent data or it represents a computation that will send data. So we have this API that's kind of lying to us. So let's try again. All right, this is a little better. This kind of is the immutable style connection, right? We set the destination and we get a new connection that represents the connection with now a destination set. We initialize some credentials, and we know that this might take a little while. There may be some asynchronous computation happening to give us this new connection state. Same with connect and same with send data. It's kind of the same idea. We're capturing the fact that a new state of our connection happens, and in this case, it's happening inside a context of a future. Okay, but using the API is a little weird if we do it this way. So here we're going to use it in a for comprehension. We can initialize some credentials. We get the new state. But then we have to make sure we connect on the new initialized credential state, right? We can't call con.connect anymore, because that's not going to work. Then we have to make sure that we now send data on the initialized connected state. So we kind of have to manage this like updated state as we go through using our API, which is a little messy in my opinion. It's error prone, right? I could forget to accidentally type the new updated state. So it'd be really nice if there was a way to thread through a state implicitly. And I'm guessing some of you know what the answer is. State monad. So I'm going to go through the basics of the state monad to start with, and then I'm going to talk about some of the limitations of the state monad and ways we can even improve the state monad. So what is the state monad? You'll learn your Haskell for great good. That says that a stateful computation is a function that takes some state and returns a value along with some new state. And the function would have the following type. Takes A, which is the initial state, and then returns a tuple of the new state and the result of the computation. So I'm going to do a really simple example with a counter. So our count state just returns a state monad that wraps our function, which is an input of int, and then it does something to the int. In this case, it's just incrementing, and then it's returning a value of the computation, which is the string representation. So now, when I use this for comprehension, when I'm calling count state multiple times, I'm implicitly getting this +1 on the state side of the computation, and then I'm returning a different value, in this case a string, which doesn't really do much, because uppercase on an integer representation doesn't give us anything. But hopefully you see the point of we now have a way to implicitly get some state changes for free. Let's talk about like the Platonic ideal of how the state monad works. I'm just going to wrap a computation that looks very similar to what we talked about in the Learn You a Haskell for Great Good. And that's going to be our F. takes an input state and returns a tuple of the new state and a computation. Kind of where the magic happens is all in the flat map. Now, if this is the first time you've ever seen state monad, you're going to want to work through this, I think, multiple times. Or read the Red Book, Functional Programming in Scala. But it is a little weird the first time you see it. So if you've seen it before, then maybe this will help make it click again or be a refresher. The flat map looks just like flat maps from anything else. Just like the flat map from option, just like the flat map from future, list, task. Your own custom flat map hopefully follows this. But the idea is you're passing in a function that takes the type of whatever we have, in this case a B, and returns a new simple state of the same state type and a new type for the result of the computation. And then it flattens that out into one new simple state of the initial state type and the result of the computation. And how does it work? Well, you kind of follow the functions. You create a new simple state. That's what it's returning. And inside that, you're chaining your old function through, passing the state from that into the result of that into your flat mapped function, getting the state out of that and passing it in to that flat mapped function. So this is where we're actually threading through all the state, right there. So that's simple state. So let's say you guys want to start using the state monad. You saw my counter example and you're like, all right, I've got a good idea to use this in production. And you start deciding that maybe I won't write my own state monad, I'll use Scala-Z state monad. And you're using it happily, and one day you get a type error, and you see it says, found Scala-Z state int string expands to IndexedState ID int string. And you're like, what the heck? That doesn't make any sense. Well, like a good software engineer, you guys want to understand, so you decide to dig into the source, right? So the first thing you're going to find is type state equals state t ID SA. All right, well, let's follow that. Let's figure out what state t is. You say type state t equals index state t FSSA. Okay, the rabbit hole goes deep, right? What's going on? Okay, we're going to look at the source. Okay, we've got an F, a contravariant input, another state, and all this other stuff. Okay, like, what's going on, right? What monsters wrote this? I don't know. But we can figure it out. We're going to go step by step to figure out what's going on and why it's actually really useful. So now we're going to do state T. And the T stands for transformer. So actually we're doing a mini monad transformer tutorial before I get to what I want to talk about. And this is going to look really familiar to my simple state. The difference is instead of returning a tuple of A and B, I'm returning an F that wraps the tuple of A and B. And what's the F? It could be anything. It could be your option. It could be your either, your disjunction, your future, your task, your custom monad. Doesn't matter, right? Okay, how does it work? Again, magic kind of happens in flat map. And we're going to see that it looks pretty much the same. In this case, it's not a lawful flat map, but we're saying we need to have a monad, meaning we need to be able to flat map the F. And otherwise, it's exactly the same. The same idea of taking this FC or the flat mapped function that handles the result of the computation and gives us a new state T, and we're merging these together by threading through the states. The only difference is we have to call flat map on the F rather than just running it. So it gives us the same idea of state, except now we have this context around our state computation, but we don't have to worry about it, right? Here's an example. Instead of just incrementing one and returning the string, I'm going to do this asynchronously on a thread pool. Maybe not the best idea, but it illustrates my point well. Count state, count state. So now we're just going to yield the new, what we're going to get is we're going to get a stateful computation that spits out a future with the updated state. So it's pretty much the same. It just handles the fact that instead of a state, we have a context around our state and our result of the computation. All right, now we get to the interesting thing, in my opinion. I think it's all interesting, but here's the more interesting part. Because nobody uses index state, and they should. So what's this whole index state thing about? Okay, let's talk about a more complicated API. This API, we'll imagine, talks to some external resource, and it's a little transactional, right? We're going to be able to view things and update things, but we have to lock them first, and then we have to commit them after we actually update them. And this kind of happens, we don't really know how it happens, but we want to have an API that just describes that this happens. And the initial state that we want to deal with is an immutable cache, right? This way we can update the cache immutably and statefully and kind of thread this cache through, so as we view things or whatnot, we don't have to re-query, and we can save some time. So what do we have? We have view, we have lock, right? This one's going to give us unit because it's kind of a side effect-y computation. We have update. It's going to give us the new item with the updated value. And we have commit. And this is going to actually like persist it, right? Or let other people see that we updated it. Okay, so what's wrong with this API? I mean, it's not bad, but what can we do with it? I'll show you kind of, this is just an example of how we can, how the API would look. I mean, this is less important, but the idea is in the state, we're implicitly updating and checking the cache. It kind of shows like a more realistic example of why you might use the state monad. We can immutably update and thread through this cached item list. So here's a usage of our API. We view an item, and then we lock an item, then we update an item. Not bad. So like I said, what's the problem? There is a problem, in my opinion. We're threading through the state, but we're not modeling it. So this is the issue. This compiles. We can view an item, we can update an item, and then we can lock an item. But that shouldn't compile, right? That's not what we designed our API to do. And we want to provide safe APIs for our users. So is there a way to make sure that this doesn't compile? Well, that's kind of why we have the indexed state monad. It's going to help us write an API that enforces how the state changes happen. So what's index state? Here's my simple index state. I may have named that wrong, but you know, simple-ish. We've got, again, a computation that takes an initial state and returns a context around a tuple. The difference is there's two types here. There's an A and a B. So that's the starting type and the ending type of the state, in addition to the computation. That's the magic. That's all the index state is. Instead of having a state that you update that's the same type, you have a state that you update that's a different type. And you can see how this actually works in the flat map. It's the same flat map, but the types just have to line up. Instead of outputting a new index state from a computation that takes our output of C with the type of A, we have to get a type that takes a B and returns a D, right? So our indexed state result of the flat map is now an AD rather than an AB, right? So we're just making sure all the types line up when we call flat maps. Otherwise, it's the exact same state monad magic of peeling out the tuple, passing in the initial, yeah, there we go. Passing in the initial value, and then threading that through to the next computation. So let's model more states. This is the way we can kind of enforce our API a little more clearly. Instead of just a cache state, we're going to have this idea of a lock state, which is the same cache data, and we have an update state. And let's see what we can do with this. So our new API, view is a cache state to a cache state, right? It doesn't change anything. We don't care how many times we view and what we do after that. But a cache state starts with a cache, or a lock item starts with a cache state and returns a locked item state. Update item requires a locked state and gives us an update state. And again, commit takes an updated state and gives us back a cache state. So now, what happens when we try to use our API? View item and then calling update item and calling lock item gives us compile time safety to make sure we're forcing our users of the API to call our API in the right stateful way. So this is the error. So this is kind of why it works. Now, I don't have time to go into the fact that IndexedState is contravariant, but that's why you're able to use subclasses to model the state. And still, we can talk about the contravariance later. So this allows us to really enforce the way we want the order of our users to call their API. So what else can we do? I don't know. This is just something we've used a little bit in one of our APIs at Verizon. I'd like to see more ideas on how we can improve this. I think it's a cool idea. I think it's underused. But I'm curious to talk to people about it if they have ideas and suggestions and criticisms. So that's Index Your State. Thanks.
Where can we find these slides?
I will put them on Scala Scale by the Bay, and I have an older version of this talk on my Twitter too. So if you go to my Twitter, it should be a pin.
Is there a way that you can look where we can see more examples of how this is implemented?
Yeah. So if you go to ScalaZ and you look up the state T, you'll have the index state, and there should be examples in there somewhere too. Yeah. But yeah.
What are the main trade-offs you've found so far, and like the things that you're looking to improve?
So I try to make type aliases whenever I'm using something like this, so people aren't scared away. But and for the first time in my life, I actually wrote like a lot of documentation on this API. Like usually in Scala, it's pretty straightforward of like, it returns a future of a tuple, right? This is the one time where I'm like, all right, let me write like a mini book to make sure people don't freak out. So there's just some training involved when your coworkers are like, I don't think I can handle this. You have to spend the time to say, hey, look, it sounds crazy, but we can do this. So that's the trade-off, in my opinion. So.
When your index type basically the same at different types protection.
Yeah.
Do you successfully attack types for that step?
I haven't thought about that. That's interesting.
So this was an internal Verizon.
The API was kind of it's similar to what an API, internal Verizon API we used. Yeah, but the index state stuff is all from ScalaZ, so that's what we're using. We use a lot of ScalaZ at Verizon. So.
Is there a way to model more than one dependency state? Right now,
I don't know. I haven't thought about it. That's interesting. All right. Thanks, guys.